Yeah, the title of today's talk is Beyond FSDP, Multimodal and Modal Parallel Training with Ray Compiled Graphs. My name is Amjad and Almahairi, and I'm a research scientist at Anyscale. This is joint work with our previous colleague, Yunxuan. So we can clearly notice recent trends in large-scale training. The first one is the use of multimodal data, such as text, image, audio, and video. In these cases, models tend to have different submodules for each modality. This is quite common in recent publications and also in the most recent Llama 2.3 release. The other trend is the use of complex parallelism strategies, such as data, tensor, pipeline, and context parallelism. And complex combinations of them, 3D, 4D, or even 5D. And final trend is the use of massive infrastructures, which involves thousands of GPUs for extended periods of time. Now, the current libraries for distributed computing actually favors homogeneous training. And what we mean by that is the case where each process executes the same program. Now, this has some limitations, and the first one we can describe as limited models, meaning that it's actually limited to homogeneous models like sequential ones, which means that it can be suboptimal for heterogeneous models like the multimodal ones we discussed before, and it's actually difficult to parallelize non-sequential architectures. The second limitations, we describe it as restrictive parallelism. These libraries actually are a great fit for SPMD methods, such as FSTP or tensor parallel. However, it's really hard to implement MPMD methods, like pipeline parallelism, where, and also it's really hard, or actually, it's actually applies the same parallelism strategy across all submodules. The third limitation is that they actually assume heterogeneous clusters, where all GPUs need to be of the same type. And it cannot really utilize different types of GPUs, like A10s, L4s, or like kind of mix of GPUs. Now, that's why we believe ray-compiled graphs actually are great for heterogeneous training, where different processes can execute different programs. What we mean by that is that this gives us like the following like advantages. The first one is we can implement flexible model architectures like multimodal models or non-sequential architectures. We can easily implement MPMD parallelism, so it's a great fit for pipeline parallelism. It's easy to implement complex pipeline schedules like zero bubble, and we can easily apply multiple parallelism strategies across our model. Finally, we can actually utilize heterogeneous clusters and which includes different types of GPUs, and basically optimize cost by distributing tasks across different GPUs. So in this talk, I will first give a quick overview of ray-compiled graphs. Second, I'll talk about an application in multimodal training, and finally, I'll talk an application about in pipeline parallelism. So what is ray-compiled graphs? It's basically, it creates a static graph of ray tasks using an intuitive ray code-like API. This static graph is actually optimized for static control flows across multiple GPUs, which is quite common in large-scale training jobs. Second, it induces much lower system overhead than the ray core. And that's because it allocates resources once and reuses for multiple executions. And finally, it supports GPU to GPU communication via nickel. So here I'm going to give a quick overview of the compiled graphs API. In this example, I will show how we can do a forward pass in a 3-layer feed-forward network on multiple GPUs. So the first step here is actually defining a ray actor for each layer. So in the code on the side, you can see you can see this block actually creates, defines an actor class, creates an actor class for every, or for each layer. The next step is defining an input to the graph, which is done by binding the input node into the first actor forward function. Third, we define communication between actors via nickel. And as you can see here, we're defining, we're annotating the activations with nickel, and then we are passing the activation into the second layer or second actor forward pass. Finally, we're compiling the graph and then executing multiple times on different input batches. So now I'll discuss an application to multimodal training. So we're going to focus on a specific case of multimodal training, which is quite common in practice. It's the contrastive vision language models like CLIP. So in this example, or in these models, we typically have two kinds of encoders, image encoder and text encoder. And we encode images and text in some feature space and then align their representations by computing a similarity matrix. One key thing to notice here is that different modalities have different compute needs. So in this case, the vision and text encoders can have very different sizes. However, because of the training objective, we're actually we're limited by having the same batch size for both modules or for both encoders, which as a result induces a significant GPU underutilization. Let's try to kind of dig deep and understand what do we mean by GPU underutilization here in CLIP. So in standard libraries like PyTorch distributed, DeepSpeed, Megatron, we place both encoders on the same GPU. So what we're going to do here next is that we're going to compute the utilized flops when training this model on an A100 machine. In this case, the vision encoder is 2.5 times bigger than the text encoder. And again, the batch size is actually the same, but it's restricted by the vision encoder, which is bigger in size. So in this plot, we're basically showing on the x-axis the elapsed time in the training and the utilized flops for during training. And we're showing 4 different boxes. The first box is the utilized flops for the text forward, the image forward, the image backward, and the text backward. And on the top, we're showing the peak flops for an A100 machine. So we can clearly see that the GPU is largely underutilized especially for the text encoder. Now, actually, this gets even worse as we train on multiple GPUs. So it's typical for standard libraries to co-locate both encoders on all GPUs and then apply the same parallelism for both encoders. Yeah. So, so in this example, we're actually training CLIP, or which is a hypothetical example where we train CLIP on 4 GPUs and apply the same parallelism for both the vision in yellow and the text in blue. And the overall GPU utilization is 22%. Now, a solution to improve this GPU utilization is actually to place the text encoder on a separate GPU, apply no parallelism to it, and then place the vision encoder on 3 GPUs and apply some kind of parameter sharding here. And with that, we can actually improve the GPU utilization up to 30%. Now, let's really try to understand what this solution offers, placing encoders on different GPUs. Now, we're taking the previous graph, but we're just plotting the forward utilization of the text and backward of the text. Now, basically, there's 2 ways to increase GPU utilization. The first one is when we apply different parallelism strategies, we're basically untying the batch sizes between these 2 encoders and increasing the batch size for the text encoder, meaning that we're going to push this box up until to reach like closer to the peak flops of the GPU. The second approach is actually to place the encoder on a weaker GPU, and in this case, we're effectively pushing this horizontal line down closer to the boxes. Now, let's look like quickly on how we can actually implement that in gray-compiled graphs. We're not going to go like in a lot of details. I'll just give you a quick overview. But here, the general idea is that in this example, we're going to place the vision encoder on a different node with 4 GPUs, and the text encoder on an L4 with a single GPU. And the way we do that in this code is that, like in these like few lines, we define those actors and annotate them with the GPUs we want them to be scheduled on. Then we're going to bind the input and pass it to all of the workers or actors that we have. Next, we're going to pass the activations, reduce them from the vision encoders, and send them to the text encoder, as we can see in the code next to it. Then we're going to take the activations from the text encoder, scatter it into the all vision encoders. And then in these cases, we're going to also directly apply or compute the backward pass. And that kind of concludes our training cycle in this model. So as you can see, it's a very short code that is not very easily implemented in any other library. Now I'll discuss some benchmark results of training a CLIP model with 1.8 billion vision encoder. In this case, it's a VIT, and a 700 million text encoder transformer. Our baseline is a PyTorch implementation, which applies FSTP4 on both encoders, and it runs on 4 800s. We plot in the first figure the throughput per dollar, meaning like how many thousands of tokens we compute per the dollar spent. In the second plot, we plot the vision GPU utilization, and the last one is the text GPU utilization. So our first method, using gray compiled graphs, actually applies FSTP3 on the vision encoder. So basically splits the text encoder on a single GPU with no parallelism, and places the vision encoder on 3 GPUs with FSTP3. And then still uses 4 800s. In this case, we can increase throughput by 23%, vision utilization by 64%, and text GPU utilization by almost 5 times. And even more, what we can do is actually we can place the text encoder on a weaker GPU, which is an L4, and use only 2 800s for the vision encoder, and apply the same FSTP2 for both models. In this case, actually, compared to our baseline, we can increase the throughput per dollar by almost 40%, and vision GPU utilization by 60%, and most impressively, the text GPU utilization by almost 17 times. Again, like our library allows us to experiment with different kinds of parallelism strategies that are different for both encoders, and we show here like different configurations, like 2D, even 2D parallelism, on one encoder, no parallelism on the other, FSTP of degree 4 versus FSTP degree 2. Now, I'll move next to application to pipeline parallelism. So just a quick overview of what pipeline parallelism is. In pipeline parallelism, the goal is to actually split the model across different devices by assigning like devices with blocks of layers. So each of these blocks or each of these like devices are actually called a pipeline stage, and then they execute kind of sequentially. But because of this pipeline that we define, we have the benefits of being able to run them run those stages simultaneously, and most importantly, we can reduce the memory usage on a single device and train much larger models. So here I'm gonna just quickly describe one of the simplest pipeline schedules in pipeline parallel training. It's called all forward or all backward. So in this example, we're actually dividing our model, splitting the model into four stages on 4 devices. So each device, or overall, we're computing 8 micro batches. So what this means is that if you have a full batch, you're going to divide it by 8 times, and then you're going to compute multiple forward passes, multiple backward passes across all the stages before updating the parameters at the end of this like pipeline cycle. Now, the core idea here is that the first device is going to execute a single forward pass on its micro batch and pass its activations into second layer and so on and so forth until you reach the last device or the last stage. And this last stage is going to execute all of the forward passes. Then at the end, it's going to start to execute the backward passes and pass the gradients back to the previous stages up until you reach the first stage. And then once you kind of execute all of those micro batches, you can update your parameters. And one core goal of pipeline parallelism is to reduce this gray area that you can see here that actually causes idle time in for each of these devices. Now, this is the pipeline parallelism is actually implemented or supported by DeepSpeed. However, there are a few limitations to this support. First is that the implementation actually is restricted to a specific kind of models, basically models that can be expressed as a list of a list of layers or sequential list of layers. The second limitation is that you are actually have to work with some predefined pipeline schedules, and in order to extend to more complex schedules, you basically need to fork the code, understand their internals, and spend a lot of time to actually get it, kind of working for your use case. And finally, you're also restricted to their training engine, and it's not really easy to customize the training logic for your specific model and pipeline schedule, and also again requires understanding very deep technical details of the library. The same also applies for Megatron. Now, let's look, on the contrary, let's look on how we can implement all F, all B schedule with Ray compiled graphs. So on the right, I'm actually showing the code that you need to write to implement an all of all B schedule for 2 workers. The first worker is on this, these are the kind of task of the first worker, and these are the task of the second worker. And so this is the code. This is the corresponding graph that actually our library builds in the back end. So what nodes here really mean are actually Ray tasks. And the edges here, we have kind of 2 kinds of edges that we define with our library. The first one is the data dependency, which actually defines the flow of data from a task to another. So in this case, we pass activations from F11 to F21, then F21 to B21, then B21 to B11. The second kind of edges here is the control dependency. And what we mean here is what these edges mean is the order in which the tasks need to execute within the single actor. So we know here that F11 needs to execute first, then F12, then B11, then B12. So next, I'm actually going to talk about a slightly more complex schedule. It's called 1F1B. And the goal of this schedule is basically to reduce the memory requirement in the AFAB schedule that we saw before. The main idea here is that each worker is going to execute a single forward pass and a single backward pass, then a single one, as you can see in this red box. Now, of course, at the beginning, there's a warm-up stage, and at the end, there's a cool-down stage. I'm not going to go into much detail here. All I want to highlight is that typically, implementing this is exposes your code into potential deadlock, and that's mainly because of the blocking nickel operations that send activations across different stages. one of the very cool features of Ray compile graph is that we can actually detect those deadlocks and resolve it for you automatically. And the way we do it in a very high level is that we're going to split a node or a task into 3 subtasks: read, compute, and write. And then we're going to reorder their execution such that we can break the deadlock. And if we cannot break the deadlock, we're going to actually give you an error and tell you, hey, revisit your schedule. Now, again, this 2 cool features that I want to highlight here is that first, we can automatically resolve deadlocks by basically doing an topological sorts on the tasks that you induce in your graph. And another important feature is overlap of communication and computation, which allows you to execute your graph in a very efficient way. Now, basically, this 1F1B schedule can be implemented in this code. And I'm not going to go into a lot of details, but I just want to highlight that the core idea of passing activations from one stage to another is implemented in these few lines of code. And passing gradients from one stage to the previous one is also implemented in these few lines of code. Of course, if you kind of wanted to do that in some other library, it's going to require a lot of much harder work to do. So a final schedule I'll talk about for pipeline parallelism is called zero bubble, and that's one of the more advanced schedules here. Again, the main idea is that we want to execute the pipeline parallel algorithm and reduce the bubble size, which is the idle time. So we're going to increase the GPU utilization as much as we can. Now, the core idea here is that the backward pass of any model can be actually divided into two steps. The first one is, or one of them is actually computing the backward pass with respect to the parameters, and the other one with respect to the input activations. So we call the first one or basically the gradients with activations, we call it B, and then the gradients with the model weights, we call it W. And again, I just want to highlight that here that if you look at this schedule of 1F1B, it takes longer time to actually execute compared to zero bubble because we are kind of reducing those white areas. And the main reason for that is because we can overlap the forward operation with either the backward or B or W. Now, again, also I'm not going to go into much detail on how we implement that, but I just want to highlight that if you can implement this complex schedule by modifying few lines of code in the 1F1B schedule. And the idea here is we simply add an additional task of W after each backward task. So now I'm going to present some benchmark results and on training Llama 2 7B on basically 4 A100 machines. Actually, sorry, 2 nodes of 4 A100 GPUs. The first one, in the first case, we show that we basically show the different number of micro batches and the throughput measured by token per second, and we can see that we can get basically in this case we're implementing the 1F1B schedule, and we can see that we can achieve very close performance to deep speed. While, as I said, it's a much simpler implementation. And our API allows us to implement zero bubble, which gives us almost 25% improvement compared to a deep speed 1F1B implementation. So to summarize, we've introduced a flexible and easy API for heterogeneous training. With our API, we can achieve almost 40% throughput per dollar gain on multimodal training over PyTorch FSDP, and almost 25% throughput gain with zero bubble over deep speed. So thank you so much. Please, if you have any questions, or don't feel free to connect with me by email or LinkedIn. Join our Slack and specifically the channel Ray Accelerated DAG. Check out what we're working on GitHub. And I just want to highlight that we are hiring great engineers to join our team. So if you're excited about the vision of developing the next distributed training library, please reach out. Thank you.
All right, for Q&A, please use this microphone so we can record your question. And
for a little while, Ray had like a workflows API that was in beta. Is compiled graphs intended to kind of replace that, or is in terms of like the kind of your DAG bindings, or is this kind of an add-on to?
That's kind of separate. I think we haven't really thought about integrations yet. It's mostly like another version of array core that is more optimized for static, graphs, static workloads.
Okay, thanks.
During training, the L4s doesn't support nickel communication, right? How do you combining like A100s and L4s and then manage the communication overhead?
We pass the activations across nodes, and I'm not really sure why you say nickel doesn't support L4. Or for
those are like cheaper GPUs.
Yeah, but they do support nickel.
Okay, nickel. Okay.
I don't know very much about nickel. Does that lock you into NVIDIA GPUs, or can you use non-NVIDIA GPUs with nickel as well?
No, it's specific to NVIDIA GPUs.
Do you have plans to figure out how to do non-NVIDIA GPUs, or?
I think this is something that we have some collaborations that we are kind of talking to about that.
Hi, I have a question about the fault tolerance. So if you compile a graph to a static execution, what if I lost a node during the execution? Will the cluster handle it, or I have to recompile?
That's a very good question. I think we are still like in an early stage of developing the library. I personally haven't really, probably some people in the Ray core team can probably give you a better answer. I think this is one of the things that we have in the back of our mind, because if you want to do really serious training, you want to handle fault tolerance. So I think this is definitely on our agenda, but I don't think we have like direct support for it.
So I have a question actually related to that one. So it's also about error handling. I know you guys are still thinking about how that should be handled. But in theory, could the compiled graph help with like elastic training, for example?
We do have actually another parallel effort in our team that like kind of supports elastic training. Again, it's still like basically a couple of months of work, so we're still like in early stages, but we really this is basically one of those, like, through elastic training we want to support fault tolerance and want to integrate with this whole ray train kind of ecosystem.
all right, another round of applause for Amjad. Thank you.